This is Nature rendition of Homework 9, Problem 2, Part 1. This is a case of a Poisson. Let n be a Poisson process with parameter lambda. P, the probability, if you will, of n, the number of random points arriving in the interval t1, t2 is equal to k. That probability is equal to e to the minus lambda t times the quantity t2 minus t1 times the fraction lambda times the quantity t2 minus t1 to the k over the k factorial. Now we are asked to find roughly 5 items. First, to draw a couple of samples to find the value where the probability is equal to 2, probability x of t equals 2. Find the expected value of x of t, find the autocorrelation of t1, t2, and determine whether or not the stochastic process x of t is WSS. Now, as we start out, we see here that x of t is the stochastic process equal to 2 if the points are odd in the interval 0 to t, and a minus 2 if they're even in the interval 0 to t. Section 1, or rather, the first section seeks a requirement of a couple of samples. Here are the samples provided. Sort of the step function, those slashes should be indicate that those lines aren't there. And then there's the corresponding step where I did not distinguish the height to relationship to 2. But there are the at least the samples at this point. Now on to the next section. This is a continuation of homework assignment 9, problem 2. This is part B, where we are asked to find the value of P of x of t equal to 2. This primarily is a situation where we have identified the odd number of points. Okay, we start out, as has been done on several other occasions, defining e to the lambda t, and this equal to the Taylor expansion of 1 plus lambda t plus the quantity lambda t over the 2 factorial plus the quantity lambda t raised to the 3rd power over the 3 factorial, which I didn't state earlier, I'm sorry, plus the quantity lambda t raised to the 4th power over the 4 factorial. We establish e to the minus lambda t equal to, using a Taylor series again, equal to 1 minus lambda t because we are setting up this particular expansion to deal with the odd numbers. So here we have minus lambda t plus the quantity lambda t raised to the 2nd power over the 2 factorial minus the quantity lambda t raised to the 3rd power over the 3 factorial. So as you can see, we are subtracting minus the odd points and retaining plus for the even points. This comes into play here, where we take e to the lambda t, and we subtract e to the minus lambda t, thereby eliminating the even points and leaving the odd points. As we summarize the expansion, we see that we end up with 2 as a result of this operation, 2 times the quantity lambda t plus the quantity lambda t raised to the third power over the 3 factorial, etc., etc. When we summarize this and we move e to the minus lambda t across the equal sign, we end up with 1 minus e to the minus 2 lambda t divided by 2 equal to e to the minus lambda t times the quantity lambda t plus the odd points. When we set this up, we were asked to find out the value of x of t when it equals 2. And here we have it where p, basically in the interval 0 to t, k is odd and is equal to the summarization odd, all the odd points, of e to the minus lambda t times the quantity lambda t raised to the k power over the k factorial. Okay, when summarized, this will break down into e to the minus lambda t times the quantity lambda t plus the odd points, which basically summarizes into this point of where p to the x of t equal to 2, this, okay, probability is equal to 1 minus e to the minus 2 lambda t divided by 2. Now, correspondingly, following the insight of what was drafted, we go back and we work toward computing the value for p of the of the Poisson equal to a minus 2, p x of t equal to a minus 2. This will be helpful in subsequent calculations. But what we do here basically is take e to the lambda t plus e to the minus lambda t, which ends up with a different summarization. The net is that p at x of t equal to a minus 2 basically comes down to being almost equal to the other finding for the probability, where this one is 1 plus e to the minus 2 lambda t divided by 2. So we have those two factors. On to the subsequent parts. Thank you. Continuing with homework assignment 9, problem 2. This is part C, where we determine the expected value of, I don't know why I keep confused, with x of t, which turns out to be, the stochastic process, but I seem to have a problem saying that most of the time. But in any event, this is equal to plus 2 times the probability of the quantity of the random variable t equal to 2 plus a minus 2 times the probability of the random variable x of t equal to a minus 2. When substituting the components for the exponential, we set this up accordingly for the odd and the even corresponding values as stipulated in the above equation. And when we summarize, we end up with the expected value of x of t equal to 2e to the minus 2 lambda t. This, in effect, rejects the notion that this particular process could be WSS because the expected value was not a constant. But for part D and T2 greater than T1, we basically have +4 and -4, the corresponding levels on the graph for the 2 points. In one case being, 2, a +2 and 2 versus a -2 and 2, and a -4 correspondingly being a plus and -2 or a minus and a +2. The autocorrelation of T1, T2, which is equal to a product of the written variables at points T1, x of T1 times x of T2, is basically equal to 4 times the probability of x of T1 times x of T2 equal to 4 plus a -4 times the corresponding p equals x of t times x of T2. When broken down even further, basically this reduces to the point that the exponents for the probabilities are substituted, and the autocorrelation is equal to did I skip? I went too far. It was equal to this 1 minus e minus 2 times the quantity of 1 minus e to the 2 pi to the quantity T2 minus T1, which is equal to 4e minus 2 pi the quantity T2 minus T1. So this is the autocorrelation. Now, although we can pursue the statistical property and look at T2 being greater than T1 and T1 equal to T2, they both yield the same auto correlation, which is 4e to the minus 2 lambda t, the absolute value, and here's where they would both apply, using the absolute value for the interval. Therefore, the corresponding requirement is satisfied. However, as stated before, this is a Poisson process, which is not WSS, primarily because the expected values are not constant. And this is true on all base Poisson processes, although processes with increments and other Poisson processes may be WSS, but this particular process is not. Thank you very much.